So, it is storming out, so there might be some noise from that. Hopefully, it's not too bad. We'll just sort of see how this goes. So, we have this sort of strange thing going on here. This is one of those problems that involves a little bit of reading, and you got to sort of store everything that's going on in the problem in your head. But basically, what you have is you've got the unit circle, and you've got, or let's see here. So if this is a unit, well, let's see here. So this is R2, and we've got like a unit circle here, and we've got this function g, which is defined on this unit circle, and it takes on the value 0 at 0, comma 1, which is here, and at 1, comma 0. And it's also g of minus x equals minus g of x. So if you've got a point here, x, then this is minus x. And so the value that g takes on at the first point is the negative of what it takes on at the second point. And that applies for every point in R2. And so in particular, these 2 points we have already, if we take the negatives, we get here and here. So we know that g is 0 at all 4 of these points. And so g is some function that goes around the circle, and it's continuous, and it takes on some value at each point here, and it takes on 0, and we've got that reflexivity. We also have this function f, which is defined on all of R2, and what we do is you take... So let's say we've got some x value here. The first thing we do is we look at this x divided by the absolute value of x. What that's going to do is that basically takes our point x and it projects it onto the unit circle here. So this would be, so this point here would be x divided by the absolute value of x. And one thing you'll notice about this is so long as x is non-zero, x divided by the norm of x will always have norm 1, and that's sort of easy to see because the size of x divided by the absolute value of x is equal to just that size of x over the size of x, which is defined and equals 1 because x is not 0. And of course here when it says 0, that means the 0 vector. So this is 0 as an element of R2. So it's the origin of this graph here. Anyway, so what do we do? So we evaluate g at this point x over the absolute value of x, and then we take that result and we multiply it by the absolute value of x. So what this thing does here is this g of x over the norm of x, that's going to give you the same thing, like if you imagine you draw a line here that passes through x and the origin, then if you choose any point which is non-zero here, then g of x over the norm of x is going to give you the same value. It's just going to be whatever it is here. Well, no, wait, that's not true. If we're over on this part of the line, then g of x over the norm of x is going to be whatever g evaluates to at this point. But if we're in this region of the line, then it's going to evaluate to whatever g is here, which happens to be the negative of what it evaluates to at the first point. So anyway, so then what you take that and then you multiply by the norm of x. So if you're on the unit circle, you don't multiply by anything. If you're really far from the unit circle, you multiply by a large number. If you multiply by a really if x is really close to the origin, then you're multiplying by a very small number. So what you should sort of imagine is that what's going to happen is, first of all, you see that if you draw any line here that goes between so we've made the observation about the values that f takes on lines of this form, and then we also see that if we get really close to 0, we're going to take the same number here and multiply by a number that's getting closer and closer and closer to 0. So we should imagine that f is going to vanish as you get to 0. So the limit as x goes to the origin of f of x is 0. And to make this nice and continuous, we actually set it to 0 when x equals 0. Okay, so now that we sort of have a little bit of intuition, we can start getting to the actual problem. So let's see here. So if we choose any particular x and we define a map H in this way, we want to prove that H is differentiable. So first of all, note that for any fixed x in R2, let's see here. The set of all points of the form Tx, where T is in R, is the line in R2 which passes through the origin 0 and the point x. So what this means is that what does H look like? What H looks like is you choose a point x here and you draw a line that passes through both x and the origin, and then when you plug in t equals 0, you're going to evaluate f at this point. If you evaluate h at a positive t, then you're going to be evaluating f at points over here on the line, and if you evaluate h at some negative t, then you're going to be evaluating f at some point over here on the line. Okay, so again, this is all just getting you used to what's actually going on in the problem and helping you see what the problem is actually talking about. So we want to show that h is differentiable. So what we see here is that if f of x equals the absolute value of x times this g of x over the size of x, then you'd imagine this thing to sort of, in some sense, give you the slope of f. Alright, I figured out a way to attack this problem. What I was going to do before was to prove that this function is differentiable at 0 and that its derivative at 0 is given by this norm of x times g evaluated at x over the norm of x. But that would only prove differentiability at 0 and not everywhere. Now it turns out that this slope should be what it is everywhere, and that's because this is actually a linear function. But if we know that we know that h is a linear function, we can prove that h is a linear function. But it turns out that if h is a linear function, then it has to be differentiable. Linear functions are infinitely differentiable because you take their derivative. Well, they're infinitely. Well, have we really talked about that yet? Well, I don't know. This is really weird because this is a really sort of easy problem, but I don't feel like we have the tools necessary to deal with this problem in an easy way. So what I'm going to do is I'm just going to prove that h is differentiable, and I'm going to prove that h is linear, and then since it's a linear function, it's infinitely differentiable, and in particular it's differentiable. Okay. So for any scalar, a, then hat equals, okay, I guess we should fix so fix x in R2 and define h as above. Then for any scalar, say a, we have hat equals, and I want to bring the a out, because if we can bring this a out front here, then we have linearity. So hat is going to be, so this is f of a t x, and so let's see here. Do we need to be careful about, we don't really need to be careful about the case when atx equals 0, because that only happens when t equals 0. And you can easily prove that that h is continuous at 0 because of what we discussed earlier about how h is just taking f of x and traveling along a particular line, and the line is given by the line that passes through the origin and the point x in R2. So anyways, if we kind of brush under the rug the issues that arise when atx equals 0, which aren't really issues, which is why we're brushing them under the rug, we have this. So this is what f is at non-origin points. And so what can we do here? What we're going to do is a trick that's sort of useful in many parts of this problem, but I might be skipping over some of them now that I'm skipping over any sort of proof of differentiability, because I'm just pushing it under, oh, well, it's linear. So what we have is we have this a divided by the absolute value of a. And if a is a positive number, again here, a is a real, so a is in R. And that's what we're using to prove linearity, because h is a function from R to R. Anyways, let me check something real quick. Alright, storms for another 40 minutes, so sorry about any noise. So, for any scalar, we have, so what happens, what is a over the norm of a? Well, if a is positive, then this is going to be 1. If a is 0, this is undefined. But when a is 0, h of at is just h of 0, which is f of 0, which is 0, so you don't have to worry about it. But otherwise, you have this, and so you have so if h is 0, yeah, so what we do is a divided by the norm of a. When a is positive, it's positive 1. When a is negative, it's negative 1. So it's the sign of a. So this is equal to atx times g of, now we have the sign of a, which is, I'm going to write as this. Then we multiply by tx over the absolute value of tx. Now, remember, g of negative x equals negative g of x. So if sine of a is positive 1, then this thing is just equal to this without the sign. But if sine of a is negative 1, then we can pull that negative 1 out front here, because that's what we're allowed to do from this equality. And what that tells us is that this is actually equal to size of atx times the sine of a times g of tx over the norm of tx. Okay, but look, we've got the norm of a multiplied by the sine of a. And if you take this norm of a and multiply it by the sine of a, you're left over with a. So this is just a times tx times g of tx over the norm of tx. But look at this thing. We know we've sort of seen this before. Remember when we went from f to g up here, we did sort of this sort of thingy. So what this ends up being is this is equal to a times f of tx, and that's equal to a of h of t. Thus, h is linear, and hence it is differentiable. Okay, cool. So now in practice, if you're actually trying to do this proof, like when I had the idea to prove, maybe we could just directly prove that h is linear. What I did was I started here and started here, and I just kept going and tried to get two things that were the same thing. So I worked forwards from hat and backwards from AHT, and that's how I came up with this string of equations. So that's how you would actually figure this out if you're doing this. But if you're writing up as a proof, it looks very nice if you can just have a string of equalities that goes from one thing to the thing you want it to be. Okay, so that does part A. So now we want to prove that f is not differentiable at 0, 0 unless g equals 0. So let's see here. So first of all, if g is identically 0, then f is identically 0, so f is differentiable at the origin 0, 0. Okay? What if that's not the case? Suppose instead that there exists some z on the unit circle such that g of z is not equal to 0. We want to prove that f is not differentiable at the origin. And for this kind of proof, again, the typical the standard in math is that you want to try to avoid proofs by contradiction when possible, but here you can't. So assume for contradiction, which I will abbreviate by AFC, that f is differentiable at the origin 0, 0. Let so here I'll just call it instead of writing df 0, 0, I'll just say d of hk, which is just the df at. So this is the derivative of f at the point, the derivative of f at 0, 0, evaluated at the point hk. So the 0, 0 tells you what point you're using to find the derivative, and the point hk is what point you're plugging into the derivative, because remember, the derivative gives you a function, not just a number. So what is this going to be? This is going to be the derivative at 0, 0. Now, we know that derivatives are always going to be linear functions. So what we can do, at least for the time being, we're just going to write this as AH plus BK. For some constants A, B, and R to be determined. So for d at hk, for the derivative d to be a linear function from R2 to R, that means that it can be written in this form. Alright, so there's some A and B and R that allow us to do this. Okay, so now what? So if we set k equal to 0, then we have the limit as h goes to the origin, not, wait, no, h is a real number. So the limit as h goes to 0 of, let's see here, so we want to look at f of h comma 0 minus f of 0 comma 0 minus d at h comma 0, all divided by the norm of h comma 0. Because this is how, if we replaced these zeros with k's, that would be how we would, and we took the limit as h and k go to 0, that's how we would find the derivative at the origin. But here we're actually only taking the limit as h goes to 0, and we keep k fixed at 0. So anyways, what we get here is, this is going to equal the limit as h goes to 0. Now, the norm of h comma 0 is going to be the same as the norm of h, so we just have 1 over the norm of h on bottom, and on the top we have, let's see here, f of h comma 0, that's going to become the norm of h times g of h comma 0 over the norm of h, and we subtract f of 0, 0, which is just 0, and we subtract d of h0, which is ah minus bk. Well, k is 0, so we have that. And so now what? Now if we take, let's see here. So this is equal to the limit as h goes to 0 of 1 over the norm of h. And then here we have, so we've got the norm of h. Well, I guess no, we don't have that. Okay, so here's what I think we're going to do this trick again. So we've got h comma 0 over the norm of h. So what this becomes is this is just g of h over the norm of h comma 0. Note that here we're writing this in 2 coordinates. So in the first coordinate we have h over the norm of h, and in the second coordinate we have 0, and we subtract ah from this. Okay, so this is going to be the limit as h goes to 0. Now here we've got this h over the norm of h again, and we can do the same thing that we did before. Here, so actually, no, let's rewrite this. Let's write this as h comma 0 over the norm of h comma 0, because the norm of h and the norm of h comma 0 are the same thing. Okay, so again, like before, we can pull out the sign. We can make this equal to just the sign of h on the inside, and then it's going to be, that will cancel out everything, and so we'll just be left with sign of h times 1 on the inside. And then as we did before, we can bring out that sign of, you know what, let me write this out, just so that it's clear everything that I'm saying. I could just sort of verbally go through it, but I mean, I have the righty thingy here. I might as well write out how this goes. So h times g. And if you don't like the pace that I'm going at, you can always just skip ahead. So we're going to end up with the sine of h times. Wait a minute. Wait a minute. What are the inputs of g? No, this is right. How did I deal with g earlier? Oh yeah, the sign is just a scalar, so we can pull out the sign of h, and then we... Right, okay, yes. So when we pull out... Okay, I'm actually really glad that I wrote this out in more detail, because I actually said something wrong when I was going through here. When we pull out this sign of h, we don't end up with just multiplying by 1. We're multiplying by 1 comma 0. Because g is a function whose domain is R2, not just R. Okay? Alright. Okay, so now we're good. And as before, we can pull out this sine of h, so we get the norm of h times sine of h times g of 1, 0 over 1, 0 minus ah. Well, wait, why did I worry so much about that? Because what's going to happen? What's g of 1, 0? 0. It just becomes 0. So all this fuss I was making about this doesn't even matter because it's just going to be 0 in the end. Okay, well, whatever. Anyways, this is limit as h goes to 0 of... So then we're going to... This whole thing drops out and we get left with the absolute value of negative ah, which is just absolute value of ah over norm of h. So this is just a. So... Since d is the derivative of f at the origin 0, it must be that a equals 0. Because this limit as h goes to 0 of this whole thing that we started with, it has to equal 0 as the part of the definition of d being the derivative. Because for d to be the derivative, then the limit as you approach the origin in any way has to equal 0. And in particular, the limit as you approach the origin with h varying and k fixed will give you 0. And so, therefore, since this gives you 0, you have to, since this limit gives you a, and the limit needs to equal 0, you can conclude that a equals 0. Alright. Oh. No more thunderstorm. Or at least no more severe thunderstorm warning. Alright, so. Now, I'm gonna sort of cheat here and just say likewise b equals 0. And I guess it's sort of cheating, but really all you have to do to prove that b equals 0 here, let me take a line or two to explain it. By setting h equals 0 and taking the limit as k goes to 0, one can prove that b equals 0. Because what's going to happen here is you're going to have the same calculation as before, but instead of h0, you're going to have 0k. And here, instead of ah minus b0, you're going to have a0 minus bk. And so the bk will be there. And then in that first term, you'll pull out the sign of k, and then you'll have g of 0, 1 over the norm of 0, 1. Which just ends up being g of 0, 1, which we know from the problem statement is 0. And so that part drops out, and you're left with the limit as k goes to 0 of the norm of bk over the norm of k, which gives you just the norm of b. And you know that that must be 0 by the definition of the derivative, and therefore b equals 0. Thus, d evaluated at h comma k must be equal to 0. Alright. So Now, so what we're going to do now is we know we have this point z where g evaluated at z equals not 0. So we're going to take the line between z and the origin and see that the derivative there cannot be 0. So let gamma be the curve given by tz, all points of the form tz such that t is in R. So this is the line in R2 which passes through both the origin and the point z. Then what we can do is we can take the limit as h comma k approaches 0 along the point gamma, along the curve gamma. And we take f of h comma k minus f of 0, 0 minus the derivative of f at 0, 0. Of course, we divide by the norm of h comma k. Now, if we're taking the limit as h and k approach 0 along gamma, then that's the same as taking the limit as taking the limit as t goes to 0 of, let's see here, now we've got 1 over tz, and then we multiply by f of tz minus, then again f of 0 comma 0 minus, well, we know that f of 0, 0 is just 0, and we know that d of 0, 0 is 0, so we can just leave it at this. And this makes sense because if we plug in tz, then we get points along this curve capital gamma, and we also know that if we take t to 0, then the value of tz goes to 0. So these two limits are exactly the same thing. So now f of tz, wait a minute, what is this limit? What am I doing now? What do I do now? I do a thing which appears to be a thing that I did from an earlier thing. All we can do is, or all we need to do is take the limit as t goes to 0 of, okay, so f of tz, so this is going to become, so we got this 1 over tz. Now f of tz is the same as norm of tz times g of blah blah blah. So we bring out a tz here, and we multiply by g of tz over the norm of tz. Okay, so those two things cancel. So we have, this is going to be the limit as t goes to 0 of g of, then again we have t over the norm of t times z over the norm of z. And so then this is going to be, let's see here, we're going to end up with the limit as t goes to 0 of g of the sine of t times, well, the norm of z is 1, so this is just z. So this is the limit as t goes to 0 of sine of t times g of z. Okay, so now what do we know about this limit? If we approach this limit from the right, sine of t will be positive and g of z will be whatever g of z is. And so we're going to end up with positive g of z. If you approach 0 from the left, then sine of t is going to be negative, and so you're going to get negative g of z, which and how does that, okay. which is yeah, of course. So g of z is non-zero, so negative g of z is not the same thing as g of z. So this does not exist. D and E does not exist. This contradicts the fact that the given limit must equal 0. And it must equal 0 because the limit as the point h comma k approaches 0 along any line as h comma k approaches 0 along any line, the limit has to equal 0, the limit of this fraction here. No matter how you approach the origin, you need this fraction to be 0, otherwise d is not the derivative. Otherwise d is not the derivative. The fact that d is the derivative at the origin means that if you approach the origin along any path, this limit will be 0, and here the limit does not even exist, and therefore it doesn't work. Okay, so this is a contradiction, and hence f is not differentiable at the origin. Okay, so I'm sorry that this has been a really sort of tricky problem to do. It really sort of intuitively doesn't seem that bad. You have just two functions f and g, and they have some pretty simple properties, and if you sort of look at the outline of the proof, you can sort of see that there's not too many difficult things going on. You just have to choose the right path to approach the origin. It's just that there's a lot of details in here that end up making it sort of messy, and you have to do a proof by contradiction, and here like you get this limit, and this limit doesn't even exist. So yeah, this is a little bit messy of a proof, but it's a proof, so we're done.